In this video, I'm going to take a look at the inverse hyperbolic functions. So to begin with here, let's just recall the three hyperbolic functions that we're already familiar with. We have y equals sin x. We have y equals cos x. And then finally we have y equals tan x. Okay. Now, each of those three individual hyperbolic functions has an inverse hyperbolic function. So for y equals sin x here, the inverse here is given as y equals r sin x. Okay. For y equals cos x, the inverse is given as y equals r cos x. And then finally for y equals tan x, the inverse is given as y equals r tan x. Okay. Now we do have to be slightly careful here with y equals cos x, in that we need to restrict the domain. Because if we think about a quick sketch here, that's my y-axis, that's my x-axis here, then it will cut through at +1. And remember, we have this parabolic shape for y equals cos x. This U shape, it will look, say, something like that. Okay? So in that case then, at this point here now, there won't be an inverse function here. Okay? So we'd have to restrict the domain here to be only positive values of x there. Okay? So we just finish up here, and x will be greater than or equal to 1. And for here, we can say this. Okay? So those are the three key points there for our inverse hyperbolic functions. We also need to be familiar with the way that we can also represent the inverse hyperbolic functions here as natural logarithms. So for r sin x, we can represent this then as a natural logarithm of x plus the square root of x squared plus 1. Okay, like so. For r cos x, here, again expressing this as a natural logarithm. This is the natural logarithm of x plus the square root of x squared minus 1. X squared minus 1. Obviously we have these same conditions here. And then for r tan x, so for r tan x here, again expressing this as a natural logarithm, this is half ln 1 plus x all over 1 minus x there. Okay. Again, same condition here. So that's everything we need to get started now with inverse hyperbolic functions. Let's take a look now at how we prove this result here and this result here. So let's start here by showing that we can write r sin x. So r sin x as the natural logarithm of x plus the square root of x squared plus 1 here. Okay. The first thing I want to do here is take y equals r sin x. Okay. So y is equal to r sin x. And what I'm going to do here is I'm going to multiply both sides by sin. Okay. On the left hand side we'll get sin y. We'll get sin y. And on the right hand side here, if we multiply r sin by sin, they cancel, they're the inverse of each other, and I'll just get left with x here. Okay, so the right hand side is simply equal to x. Now what I'm going to do is use the exponential definition here for sin y. So in that case then, you can see that x is equal to e to the y minus e to the minus y all over 2. Okay? And what I want to do here essentially is get all the way to y equals. So we just need to make y the subject here. But clearly from this point here, there's a bit of work to do until we get it to that point. Now the first thing I'm going to do here is multiply through by 2. We get that e to the y minus e to the minus y is equal to 2x. What I'm going to do now is just simplify this left hand side here. So this is the same as minus 1 over e to the y. But what I'm going to do then is multiply through on both sides by e to the y. Now we'll get rid of that fraction there. So I'm going to get e to the 2y. This would be minus 1. That will be equal now to 2x e to the y. Okay. And what I want to do here now is set this equation equal to 0. Okay, we're going to solve it. I want to set it equal to 0. So I'm going to subtract 2x e to the y off both sides. We get e to the 2y minus 2x e to the y minus 1 is all equal to 0. Okay? And what I actually have now is a quadratic here. Okay? So basically we need to solve this now. Now it's up to you how you go about this. What I'm going to do here is I'm going to complete the square. Okay? So if I complete the square on this quadratic here, what we're going to get is we're going to get e to the y minus x. Okay, we'd have this coefficient here, so minus x. We'd square this bracket. We now subtract this here squared. So that's going to be minus x squared. And then don't forget the minus 1 here. And that's all equal to 0. So what I'm going to do here now in this case is take this minus x squared and this minus 1 over to the right hand side. We get e to the y minus x all squared is equal to x squared plus 1 there. Okay. Now clearly I want to get rid of this square here, so we need to square root both sides. So we finish the question up here. I'm going to square root both sides now. On the left hand side we'll just get e to the y minus x, e to the y minus x. Now on the right hand side here, don't forget we get plus or minus, so plus or minus the square root of x squared plus 1. Okay, and in that case then, we need to add x to both sides. So I'm going to get e to the y is equal to x plus or minus the square root of x squared plus 1. Okay, now we need to consider here whether we include both solutions. Now clearly we're not going to, because we can see that the final solution here only includes the positive solution. And the reason for that is because in this case, if I take the negative solution here, there could be a chance that this would be less than or equal to 0. And clearly there is no solutions or no values of y such that this can be equal to 0 or less than 0. Okay, so in that case, we omit the negative solution and we get that e to the y is equal to x plus the square root of x squared plus 1. Okay. Now remember, all we want here is y, like we said at the beginning, we're making y the subject. So in that case then I need to take the natural logarithm of both sides here. What we get then is y equals, that's therefore dots apparently, y is equal to the natural logarithm of x plus the square root of x squared plus 1 there. Okay, so we're nearly done. Remember, we want to show that r sin x is equal to the natural logarithm of x plus the square root of x squared plus 1. We're pretty close. Remember, we've got y equals, so how do I get the r sin x here? Well, we'll go back to the original expression that we started with here, or the original equation of y equals r sin x. So therefore, if y is equal to r sin x, just substitute that into y here. We get r sin x. So r sin x is equal to this natural logarithm. X squared plus 1. And there we have it. So that is as required. Okay. So there we have it. So what we're also going to do now is show how we'd find the inverse hyperbolic function there, or express r cos x as its natural logarithm. So let's take a look at that now. So let's take a look now at showing that r cos x, so r cos x here, can be expressed as the natural logarithm of x plus the square root of x squared minus 1 there. Okay, so again, all I do here is I begin with y equals r cos x. So y is equal to r cos x. Now what I'm going to do here is multiply both sides by cos. So on the left hand side we're going to get cos y. So cos y. On the right hand side here, if we take cos of r cos x, and in that case, the cos and the r cos will cancel. They're the inverse of each other. I'm going to simply get left with x. Okay. So what I can do now is express this here as its exponential definition. So in that case, x is equal to e to the y plus e to the minus y all over 2. Now again, from here, what I want to do is make y the subject. So again, first thing I'm going to do here is multiply through by this 2 and get rid of this fraction. We get e to the y plus e to the minus y is equal to 2x. And what you'll likely see from here is a lot of the steps now follow the same pattern as what we saw for the previous example. So in this case, this is 1 over e to the y. I'm going to multiply through now by e to the y. So we're going to get e to the 2y. So e to the 2y, this will be plus 1. And then I'm going to get 2x e to the y. Now again, sounds pretty repetitive, but we're just going to subtract this 2x e to the y off. I'm going to get e to the 2y minus 2x e to the y plus 1 is equal to 0. And again, from here, all I need to do now is solve this quadratic. Okay. So again, what I'm going to do here is I'm going to complete the square. So in that case, I'm going to get e to the y. We get e to the y minus x. Remember, we halve this coefficient. We square this bracket. Now subtract this squared. That's going to be minus x squared. This time it's plus 1. And that's all equal to 0. So from here now, what I'm going to do is add x squared to both sides and subtract 1 off both sides. I'm going to get e to the y minus x all squared. But then I'm going to get x squared minus 1 here on the right hand side. Okay, so x squared minus 1 there. And again, what I want to do is get rid of this square now. We do that at the top here. I'm going to get e to the y minus x. And that's going to be equal now to the plus or minus. We need the positive and negative solution here to x squared minus 1. Okay. Now, remember that our cosh x is always non-negative for all values of x that are strictly greater than 1. So what I'm technically considering here is if I add x to both sides, I'd have e to the y is equal to x plus or minus the square root of x squared minus 1. Okay. So if we were to consider now just a negative solution, that would be x minus the square root of x squared minus 1. And that's going to present us with a bit of an issue. Okay. So if that's strictly less than 1, we have an issue. So in that case, again, we're going to omit the negative solution. Okay. So what I'm going to get left with then is e to the y is equal to x plus here, so only the positive solution, plus the square root of x squared minus 1. Like we said before, we just want to make y the subject here. So I want to get rid of this exponential. And so yeah, we take the natural logarithm of both sides. In that case, then we get y is equal to the natural logarithm of x plus the square root of x squared minus 1. But remember, we're not done here yet. We want to show that our cosh x is equal to this natural logarithm rather than y. But we know that y is equal to our cosh x. So therefore, in that case, our cosh x is equal to the natural logarithm of x plus the square root of x squared minus 1 there. Okay, and there we have it. That's as required. So as required, and that gives our solution there to the second example. Not really a solution as such, but more of our proof or derivation. There we have it. So that actually brings us to the end of this video on the inverse hyperbolic functions. In the next video, we're going to start taking a look at the identities for hyperbolic functions.